thing, so it should be okay. Okay, you can.
Okay. Yeah, hello everybody. I'm Liu, and I'm a technical support in work in Qingteng AE Institute, and it's a glad to have this opportunity to share these presentations. And first, I'd like to say thanks the organizers, all the supporters behind this. They're doing a great job, and it's a so let's slide. Yeah. So my talk today is of things acoustic emission for unattended quantitative leakage monitoring. And there will be 4 parts. One is traditional method of leakage detecting, and 2 quantitative experiment of leakage detecting, and the online water pipeline, a quantitative leakage monitoring simulating experiment. And then the conclusion. Yeah, first is the valves and pipelines. As we all know, it's everywhere. It's widely used, and the erosions and corrosions, blah blah, say cause leakage and accident, and the economic losses. So we all know that. So it's just skip this. And there's some traditional detecting methods like direct check, on-site negative pressure wave detection, and others. So there are some common disadvantages. It's a professional. They need professionals on set. They need to check point by point, or even need to dig and check the buried pipelines, and the cost high labor intensity and the low work efficiency. So we need a new technology to do this job. So uh, uh, there's a new technology. It's called Internet of Things AE technology monitoring system for leakage. Yeah, look at the picture. This system is combined AE technology with the internet. The left one, the sensor, is the sensor can receive the leakage signals and give the signals to the processors, which is we call this RAEM1, and these processors can analyze the signals, data from the uh, leakage signal, and also it can judge the leakage level, which were set at the beginning, and then through the internet communication with the 4G, Wi-Fi, or Ethernet, or anything you want. So we can send the data to the cloud, and the system can send the alarm message and to user terminals automatically. And also you can log in the platform to check every alarm information. So this is the theoretical basis. As we can see in picture, this is a simulating picture of the leakage. So there are 3 areas will be caused by the leakage. So first is the mixing zone and transition zone, and then it's a fully developed zone. And the leakage AE signals are mainly generated in the turbulent mixing zone, is like here, and transition zone is here. And high frequency frictional impact signals are mainly generated near the leakage outlet, outlet. And low frequency oscillation signals are mainly generated in the position far from the outlet here. And when pressure difference increase, the impact signal caused by the leakage blocking will be generated, which is much higher than the turbulence signals. And these signals can be used as meaningful signals for detection. So we do the quantitative experiment of AE leakage detecting. We choose a submersible as the experiment object which is a big air bottle with the ball valve and pressure gauge on it. We also use the air compressor and the flow meter as the auxiliaries. And data acquisition equipment, which is the SAEU3H acquisition system, has to be the equipment. So we can see the pictures. This area is the ball valve, and this is the sensor. It's very near the ball valve. And this is the SAEU3H acoustic emission system. It's a sensors, preamplifiers, and the cables, signals, processors, analysis software is like other common equipment. We get the sampling setting here in this small table. It's a sampling rate, HTT, HLT, ET, and threshold is 23 dB. Then first experiment, we name it, is a quantitative relationship between different leakage amount and AE parameters and the same pressure difference. It's a little bit long, but it's not difficult to understand. So the procedure is first we mounted AE sensors near the ball valve and connected the AE system and keep AE system sampling continuously and control the leakage rate by adjust the ball valve, which could be measured by flow meter, and keep the leakage rate remain stable in the following stages. First, we increase the leakage rate and then decrease until it's 0. And here in this place is we get mistake, so we choose the wrong flow meter is too small. So in this place we change the big one. So and we go on the experiment. Yeah, after sampling, here's what we get: all the parameter data along with the leakage rate, as we can see here. It's become bigger, and then to go down is other parameters. It's the same change. In this picture, this is the waveform. This is a part of a waveform, the increasing part. As we can see, the waveform is getting bigger, stronger, step by step with the leakage. Except this area, this we can ignore this because this at the time we are replacing the flow meter, so it's get some abnormal data. And this also is different parameters in time domain under different leakage rate. As we can see, here is it's the same with the waveform. It's go up step by step. Yeah, this picture is the typical frequency domain. It shows that the leakage AE signals, the frequency is mainly about 10 to 80, 10 to 80, 85 kilohertz, mostly. Yeah, here is the second experiment we've done. The named quantitative relationship between different leakage amount and AE parameters and the valve opening, but different pressure differences. So the procedure is first keep the ball valve open throughout the experiment, and the tank pressure was shown on the pressure gauge. And third, reduce the tank pressure step by step down by the other exhaust valve and the remaining pressure at following stages. We decrease the tank pressure from the 0.42 MPa until it's almost 0. It's 0.02 MPa. So after sampling, and we also get some the data with the tank pressure, the leakage rate, the amplitude energy, RMS, and the ASR is directly calculated by the bed computer, the bed pressures, AE pressures. And this is original correlation diagram in time domain. As we can see here is some noise here. Yeah, because we release the tank pressures, we turn the valve, so there caused some noise. So after filtering process, yes, we get this. As we can see clearly, the AE signal data is also as a decreased step by step along with the tank pressure. And also here's the linear correlation diagram between pressure and different AE parameters. Yes, it's a monotone increased with the tank pressure. So we get some summaries here. Yeah, leakage AE signals frequency is mainly about 15 to 70 kilohertz. And leakage signal parameters are monotone, increase or decrease along with the leakage rate. Energy, RMS, and ASL could be used as the criterion of leakage quantification. And ASL is the best. And in valves and pipelines or tanks, the medium inside and pressure difference, size of the leakage source, and position of sensor and other factors directly affect the AE signal characteristics. So we need to calibrate the AE monitoring system before using. So then we get one online water pipeline quantitative leakage monitoring simulation experiment. So we choose the water type and the water pipeline to simulate the water leakage. Like this picture, this is the processors, and this small one is the sensors. Yeah, it was installed on the next to the water tap, and we used the process named RAEM1 to do the processing job. And this small table is the sampling setting. The threshold is the 30 dB. Yeah, this is the introduction of the REM. It's a single channel or multi-channel. It's a selectable based on Linux system and 24/7 stable running. And the assembly parameters is 2M and 16 bits. And the sensors is a built-in or a built-out, and with the preamplifier built-in or out. And threshold triggers and time triggers and power supply. The battery built in or built out is selectable. And the communication, now we can use the Ethernet, the Wi-Fi, the 4G, the RS485, etc. And you can choose other communication ways as you want. So before the experiment, we do the system calibration. So we need to turn on the water tap at different angles and measure the water with a measuring cup. The relationship between the leakage rate and ASL are shown in the below. In this table, we see the data here, and also we use the data to create the linear correlation diagram between ASL and the leakage rate. Yes, we can see the slope is almost straight. So using all this data, we can create a formula between the leakage rate and ASL. So then we input this formula in the monitoring system. Then the system could calculate the leakage rate automatically. Then we could log in the cloud server platform to view real-time data. So as shown in the left picture, yeah, it could be seen clearly the time that leakage occurs is here, and the corresponding leakage rate. It's about 47 something, and the time is 17 and 42. And also, we could set alarm levels in the cloud platform, and the level rules of this stimulating experiment were as below. It's level 1 to 4, and it's the corresponding leakage rate. And also this picture, the red picture, is the example of setting of level 2. We can see here, we have the trigger 1. We also add some other triggers. This is the leakage rate. It's between 10 to 20. That means level 2. So it has the action here, the alarm output, and we can also give it some other alarm. Then we receive. It's very easy to set. Everybody can do it. And then when the alarm condition was reached, the system sent the alarm message or email to your smartphone automatically. You could also log in the server platform through the smartphone or computer to view and process the historical alarm information. I see the pictures. The left one is the alarm message. Send it to your phone, and the right one is the use the smartphone to log in the platform. You can see the historical alarm here, and also we can take actions to face this problem. So we get some conclusions here. The Internet of Things AE system, or AEM1, could realize the long-term unattended quantitative leakage monitoring. And massive AE data could be processed and converted into simple and understandable leakage levels so that users who do not understand acoustic emission could quickly get started. And data processing is centralized in the processor. Only a small amount of data is output or uploaded, which can effectively reduce the requirement of data communication, speed, and equipment costs. And the advantage of long-term stable operations, automatic alarm, quantitative monitoring, and low cost are meaningful to application of leakage monitoring. So this is all what I shared today. So thanks everybody.
Thank you very much, Mr. Liu.
Yes.
The paper is open for questions and discussion.
Okay.
Any question? Yes, we have one.
Thank you for the presentation. Abdelkim Saidon from CITIM. I had just a question about the relation between the leakage rate and the ASL. I didn't understand well how you establish this equation.
You mean the formula?
No. You can return to this one. The L is the rate, liquid rate, right?
Yes.
Okay, and what is K?
Yeah, K is the assume the it's assume the K. Yeah, B also. ASR is the we know.
You mean it's
we assume
corrective
K.
coefficient? Okay.
Yes.
I didn't understand how you established. Yeah, maybe from the diagram before.
Yes, the data here.
Okay, I understand.
Yes,
okay.
We can see here there's a straight slope.
Okay.
Between the leakage rate and the ASL, right?
but is it true only for the experimental setup that you did, or it's true for all the liquid?
It's no, it's just for this experiment. So because every experiment is it's different, right? So every formula is different. So every time we use this monitoring equipment, we need to do the calibration work every time before using.
And what is the conclusion that we have to take from this equation or from this coefficient when we do calibration of your system? When we can say that calibration is okay and it's not okay? How much is the coefficient for the two situations? I don't know if my question is clear.
After we, I know what do you mean. So it's good. After we input this formula, and we can also recheck again.
Okay.
Yeah, you know what I mean. We can
okay.
give it the leakage, give it the real leakage.
Okay, I understand.
You understand? Yes.
Yeah, just a linear. Okay, thank you very much. Thank you.
Thank you very much.
Welcome.
We have to move to the next paper. We hope to have you here in the next UGA so you can present it live and have the time also to speak during breaks with the people. Thank you very much again for your participation.
Welcome. Thank you, guys.
We have to move to the next paper. It is